Hello and welcome to this video presentation. I'm Teitsma,
And I'm Jaxon, Wright.
and today we are going to be talking about smartphone processors and the various technologies that have gone into making them what they are today. We're going to start by talking about the early days of smartphones. Back in 2007, Apple released their first smartphone, known as Apple's iPhone, and HTC released their first one, known as the HTC Dream or T-Mobile G1. Both of these phones had single-core CPUs. It was clear that with these phones' success, there is going to be a high demand for small, power-efficient, and high-performance CPUs. In 2008, Qualcomm announced their first SoC, or System on Chip, that was designed for smartphones. The technology that goes into developing mobile SoCs has increased dramatically. The technology is becoming more and more sophisticated and can support up to and even beyond 8 CPU cores. You may be wondering what a System on Chip actually is. Smartphones are constantly increasing in size. Apple's first iPhone had a display size of 3.5 inches, while now the iPhone 6 Plus has a display size of 5.5 inches. This increase in size does mean more space for hardware, but this has mostly gone to increasing the battery life of the phone through larger and larger batteries. The picture shows a broken down iPhone 6, and this red box is what is called the SoC. The small chip contains many essential functions that the smartphone must complete, such as audio, video, and graphics or data processing. SoC is a technology that had already been around for decades in things such as digital watches, and with the increased popularity of smartphones and the increasing demand for battery life and performance, it was only a matter of time before SoCs became an integral part of every smartphone. An SoC is essentially one chip that does it all. Rather than having a motherboard and separate chips for handling the different functions, it puts it all on one small chip in order to save space and increase efficiency at a minimal cost or even increase in performance. Most smartphone SoCs contain ARM CPU cores. ARM licenses out their design to different manufacturers who utilize the CPU cores with other various hardware pieces on their own SoCs. Some manufacturers even have research teams that work on optimizing the ARM cores that help to improve the efficiency and/or performance of the CPU even above the standard ARM designs. This graph displays the sales of chips containing ARM cores. As you can see, shortly after 2008 and 9, when SoCs were becoming more and more popular in smartphones, in 2010 there was a large boost. This was because the iPhone 4 was released in that year, and also Android smartphone sales surged 888% during that year. This increase in market size led to an opportunity for many new hardware manufacturers to enter the smartphone marketplace.
On the market today, there are many different brands of mobile CPUs, such as Qualcomm Snapdragon, Samsung Exynos, MediaTek, NVIDIA Tegra, the Intel Atom series, and Apple's A series. All of these SoCs use the ARM architecture, except Intel, who has their own proprietary architecture. In 2014, Qualcomm's Snapdragon line dominated the global market revenue share. Because of this, we're going to focus on a specific version of Qualcomm Snapdragon 800 series. We'll be focusing on Qualcomm Snapdragon 808. This chip features 6 64-bit cores, 4 of which are ARM Cortex-A53s clocked at 1.44 GHz, and 2 ARM Cortex-A57s clocked at 1.82 GHz. It also features ARM's Big Little technology, which we'll explain later in this presentation. The Snapdragon 808 is on devices such as the Moto X Pure Edition, the Nexus 5X, the LG G4, LG V10, and the BlackBerry Priv.
The Snapdragon 808 contains 2 AMD Cortex-A57 cores. This is a block diagram of the Cortex-A57, which as you can see has a fairly deep pipeline at 15 plus stages. After the instruction decode stage in the pipeline, it has a global branch predictor, which has a branch target buffer holding from anywhere from 2,000 to 4,000 entries. This is a superscalar processor containing 8 separate data paths. These paths can all be occupied in parallel. 2 of them are for load store operations, 1 is for multiplying and dividing integers, 2 are for complex instructions, one is a branch decider, and the final two are simple integer ALUs. It also has split L1 caches, a 48 kilobyte instruction cache that is three-way set associative, accessed primarily by the branch predictor and normal instruction fetching. And the data cache is 32 kilobytes and two-way set associative, accessed mainly by the load store operations in the superscalar pipeline. The unified L2 cache is up to 16-way set associative and can vary all the way from 512 kilobytes to 2 megabytes. The instruction decode phase also handles register renaming in order to get rid of write after read and write after write hazards by using registers that are not accessible to the programmer.
As stated previously, the Snapdragon 808 utilizes ARM's Big Little technology, which takes advantage of the dynamic usage pattern for smartphones and tablets. These usage patterns can be simple, such as texting and web browsing, or complex, like gaming or using 3D intensive programs. It does this by having multiple cores of differing sizes and capabilities. The little cores handle the simple stuff, like texting and web browsing. The big cores handle the 3D intensive stuff that needs more power. The primary goal of ARM's Big Little technology is to significantly improve battery life by only using the cores needed for the task at hand. It does so without hampering overall performance. This is essential because processing technology has advanced at a much quicker rate than battery technology has. Since battery life holds such a high priority in the smartphone world, Big Little has fundamentally changed the game by enabling increased efficiency and performance without the expense of battery life. As you can see, on the left we have a simple Google search within Chrome. On the right we have a part of New York City shown in Google Earth. The Google search requires little processing power, as you can see by the low clock speeds and one of the big cores being completely offline. The Google Earth, which is rendering 3D buildings, clocks the little cores all the way up and the big cores close to max. However, it is worth noting that some of these numbers would be different if these were the only things running at the device at the time. Now we'll dive a little bit deeper into the different types of Big Little. The first and most basic type is cluster migration, also known as cluster switching. In cluster migration, the operating system can see one of two processor clusters at a time, that is, all the bigs or all the littles. Only one of these clusters can be active at a single time. Since that, tasks run either just on the little cluster or the big cluster. This is not ideal because you can't use bigs and littles together at the same time. The next type is called CPU migration, also known as in-kernel switching. The operation scheduler can see 4 CPU pairs, but only one CPU in each can be active at one time. Tasks can run on either the big CPU or the little one paired with it. This is better than cluster migration, but still does not use Big Little to its fullest potential. The Snapdragon 808 utilizes a form of Big Little called heterogeneous multiprocessing, which is also known as global task scheduling. This is the most powerful use model of Big Little, which enables the use of all physical cores at the same time. Threads with high priority can be allocated to the big cores, while the threads with less priority, such as background tasks, can be performed by the little cores, maximizing performance and battery life. In the Snapdragon 808, it has a cluster of 4 Cortex A53s, which are the little processors, and a cluster of 2 Cortex A57s, which are the big processors.
One of the first issues that comes to mind when talking about how to implement Big Little technology is how you can make the CPUs accessible to the outside world, as in you do not want to shoehorn yourself into having too specific of an interface that you have to develop a new application for every single type of core clusters you would find. This issue is overcome by something called the cache coherent interconnect. This is something that talks to both CPU clusters, and it looks like one multi-core processor to the operating system and the user software that uses the CPU. ARM has also released publicly the global task scheduling software that they have used in order to implement Big Little technology. This makes it extremely easy for the manufacturers or OEMs to integrate it quickly into their own SoC. The diagram on the right shows a block diagram of a system on chip. The orange box contains the two clusters of CPU cores that feature the Big Little technology. They're both connected to the cache coherent interconnect, which in turn is the main driver for the entire system. The cache coherent interconnect is the glue which holds all of the different parts of the SoC together. It is connected to the CPU cores, as mentioned before, the GPU, RAM, and display and video subsystems, and much more. The cache coherent interconnect is most likely going to play a crucial role in optimizing SoCs. The key concept of the interconnect is to maximize the efficiency of data movement and storage, which can deliver the performance needed at the lowest possible power. There are many factors to consider when talking about how to improve the performance or efficiency of smartphone CPUs. Unfortunately, it's not as easy as just adding another core or increasing the clock speed of the existing cores. This graph displays the power consumption of Samsung's Exynos 5433 Cortex A57 cluster on its SoC. It's easy to see on the x-axis that as the frequency of the clock increases, the power consumption of the core also increases. However, the most notable thing about this graph is that as the number of cores increases, so does the power consumption. While adding another core may increase the performance of the system altogether, it would increase the power consumption of the system, which in turn would decrease the battery life of the phone. The things that need to be considered when discussing the number of cores that need to go into the SoCs is how often the user is going to be using all of the cores, and whether or not that peak in performance during those high usage times would be worth a slightly higher power consumption overall. The main thing to take away from this is that mobile processing has a much greater limitation placed on it than other types of processing, because they have to work in a much more battery depraved environment. Desktop CPUs are able to focus much more heavily on performance and not as much about efficiency. That's why mobile CPUs have to come out with more and more technologies to increase the efficiency, which will in turn allow the performance to increase. This is seen through ARM's Big Little technology. Today's mobile devices are expected to do it all, handle complex processing for voice, video, and games. As technology is constantly advancing, the expectation and necessity of small, power-efficient processing is going to be at an all-time high. ARM's Big Little technology is just one way that this is being achieved today. With nearly 2/3 of Americans now owning smartphones, the competition will only increase the drive for new technological advances in the mobile front that will be in your pocket in the upcoming years. Thank you for joining us today for our presentation. I hope you enjoyed our overview of smartphone CPUs.